Hello Math 10 and welcome to Chapter 4. So you should have this little handout here which is the introduction to roots and powers, and we want to try to avoid using a calculator. So hello Math 10. So what we're going to look at today is we're going to look at square roots. Chapter 4. So you should have this handout here. So now square roots this is going to be about a 5-10 minute lesson. Let's just review a few ideas that we have with powers. Now, roots and powers is something you're already pretty familiar with. The square root of 9 is equal to 3. Let's go through and have a couple of look at a couple of ways that we can go through and express this idea. If we have something first like the square root of 9, if we know that 9 is a perfect square as being in its prime factored form, we know that the square root of 9 is equal to 3, isn't it? So we've got the square root of 3 times 3, word here, which we could think of as being the square root of equivalent 3 to the power of 2, and of course the square root of 3 to the power of 2. Now this is interesting here because the square root reverses the effect of squaring. And so that's equal to 3. In fact, what we do say is we say that the square root as an operation and squaring as an operation are what we call inverse operations. Now, we have inverse operations in other parts of mathematics as well, don't we? 3 times 4 is equal to 12. Can also be expressed using the inverse operation of multiplication, which is division. 12 divided by 4 is equal to 3. Now, let's think about this. Let's come up to our statement up here again. The square root of 9 is equal to 3. That's what we call equivalent to saying, now there's a new sign for you, a new symbol, and that symbol there we say is equivalent. So it's equivalent to saying 3 to the power of 2 is equal to 9. So we want to, one thing that we want to do in part of the exercise here is we want to be able to go through and express square root statements as their equivalent square statements. Now, let's come over here. Now we're told here that we want to go through and we want to use, sometimes if we can, we use prime factorization to go through and evaluate these squares. So let's look at the first one here. We've got the square root of 64. Now, we know that the square root of 64 is equal to 8. But let's have a look at it using, thinking of it in terms of prime factors. So, square root of 64. Well, hopefully, I've sort of done this in advance here. 2 times 2 times 2 times 2 times 2 times 2, I believe it is. Okay, so 2 times 2 is 4. 4 times 2 is 8, 8 times 2 is 16, times 2 is 32. Yep, that's right there. Now, let's have a look at it. So there it is written as its prime factors. The square root of 2 to the power of 2, if I take that group there, 2 to the power of 2 for the second group, 2 to the power of 2 for the third group, isn't it? Now, what happens here? The square root of 2 times 2 is just 2. 2 times 2 again is just 2. The square root of 2 times 2 again is just 2. And there we have it, 2 times 2 times 2, which is equal to 8, isn't it? Let's take another one. Let's take the square root of 625. Now, once again, if you just simply put that into your calculator, you're defeating the purpose of what we're trying to demonstrate here. 625 is actually a perfect square, but let's go through and break it up into its prime factors here. So 625 doesn't divide by 2, 3, 4, but it divides by 5. 5 times 125. All right, and we do 5 again. 5 times 25. We do 5 again, and it's 5 times 5. And then lastly, we've got 5 times 1. So here's our prime factorization there. So we can say this is the square root of 5 times 5 times 5 times 5. Now, think of it like this. 5 to the power of 2 times 5 to the power of 2. And what does the square root do? The square root inverses the square. So the square root of 5 to the power of 2 is 5. 5 to the power of 2 again is 5. And there we have it. That's equal to 25. So the square root of 625 is equal to 25. Now, let's check out a couple more examples here and how we could do them using prime factors. Let's have a look at this one here. We've got the square root of 9 times 16. So if we went through and expressed that as 9, okay, as prime factors is 3 times 3. And 16, well, that's 2 times 2 times 2 times 2. Now, look at this. The square root of 3 times 3, okay, is just equal to 3. Then we've got the square root of 2 times 2, which is just 2. So we've got another factor of 2. The square root of 2 times 2 again, we've got another, let's just move it sideways a little bit here, so another times 2. So the square root of 9 times 16 is going to be equal to 3 times 2 times 2, and that's equal to, 3 times 2, that's equal to 12. Now check it out. If you'd gone through and evaluated 9 times 16, square root of 144, which is equal to 12. Now, we'll look at another one here. Look at this here. Ooh. Number 12 here is the square root of a negative number. Now, you may have encountered this before, but the square root of a negative number is a little bit of a problem, isn't it? Square root of negative 4, or any other negative number. Now, some people say automatically that that is equal to negative 2. And don't think too much about it. That doesn't seem to present much of a problem. But what would be the equivalent squared statement? If this is true here, that would mean that negative 2 raised to the power of 2 would have to be equal to negative 4. But look, negative 2 raised to the power of negative 2 is negative 2 times negative 2, which is equal to positive 4. So guess what? The square root of a negative number has no solution, at least in the set of real numbers. So that cannot be, if you try putting that in your calculator, it's going to come up with an error message for you. All right, so in the set of real numbers, we can't find any square root of a negative number. Now, the next thing we're going to look at here is we're going to look at cubic roots. Now, let's take an example. So, if we looked at the cubic root of 8. Now, your calculator has a cubic root button, which is nice, but if we put that into our calculator, we would find that this is just equal to 2. In other words, 8 happens to be a perfect cube. Now, this would be the equivalent of writing, there's our sign again, if we take the number 2 there, we raise it to the power of 3, that's equal to, well, look at it, it's 2 times 2 times 2, and that's equal to 8. All right, so just as we did with square root and square statements, we can do equivalent cubic root and cubed statements. So, look at this again. The cubic root of 8 is really the cubic root of, in terms of prime factors, 2 times 2 times 2. So every group of 3 there, we take the cubic root of that, and that's just equal to 2. Let's look at another example. So let's take something like, let's have a look at number 13 here. Now, we've got the cubic root of 8 over 27. Now, if we think of it in terms of prime factors, that's the cubic root of, well, 8 as prime factors is nice and easy. 2 times 2 times 2. 27 as prime factors, 3 times 3 times 3. And check this. The cubic root of all of those, 3 of them grouped together, is just 2. The cubic root of 3 times 3 times 3 is just 3. And there we have it there, don't we? Now what's interesting is that we've got some here that involve negative numbers. Look at this. We've got the cubic root of negative 27. Let's just pop in a page here. Cubic root of negative 27. If that were a square root, of course, we know there's no solution. Now, if you were to put that in your calculator, that's just the cubic root of, well, we can just put in negative 3. Now, why does that work? Well, if we take negative 3 and raise it to the power of 3, now look at this, negative 3 times negative 3 times negative 3. So we've got 3 negatives. Now, this pair of numbers becomes positive 9, negative 3 times negative 3, and then we've got times negative 3, which gives us negative 27. So whereas it's not possible in real numbers to have a square root of a negative number, it is possible to have the cubic root of a negative number. All right, now let's take another one here. Let's take something like the cubic root of 125. Now, if you broke up 125 into its prime factors, all right, we can divide by 5 times 25, and then we can divide by 5 again, so 5 times 5, and then we've got 5 times 1 like that. So we've got the cubic root of, there are the prime factors there, 5 times 5 times 5. So 5 times 5 times 5, which can also be thought of as being the cubic root of 5 to the power of 3. And once again, we see that inverse effect, don't we? The cubic root of a cube gives us just the number 5 there like that. Okay, we'll check out one more here, and then you can start working on the exercise. Let's have a look at this one here. We've got the cubic root of 54 over 2. Well, one way to do this would be to go through and simplify 54 over divided by 2. Well, that's equal to 27. And then thinking about it in terms of prime factors, it's the cubic root of 3 times 3 times 3, which is just equal to 3. So there are some examples for you to work on. Let's just look at the last page of this little handout here. All we're doing here is we're writing equivalent statements. We've already talked about this. All right, so what would be the equivalent of saying the square root of 196 is equal to 14? That's equivalent. You can write the sign in there. 14 to the power of 2 is equal to 196, isn't it? Let's take another one. Okay, number 4 here. We've got 2 to the power of 5 is equal to 32. Now this is interesting. What would be the equivalent statement writing a root? Well, if it's to the power of 5, we can talk about the 5th root of 32 is equal to 2. Now, when we're talking about the 5th root, we're thinking about, well, what number multiplied by itself 5 times is going to equal to 32? Well, it's that one there, isn't it? Okay. So there are some exercises for you to work on ready for next class.